What would happen if you accidentally fell into a black hole? Well, the question feels like a whisper from the deepest, darkest part of space. It is a thought that both terrifies and fascinates us. It pulls at our deepest curiosity about the universe and our place within it. These cosmic titans are not just science fiction. They are real objects, scattered across the galaxies like dark jewels. They are places where the laws of nature as we know them are pushed to their absolute limits. To imagine falling into one is to imagine a journey to the very edge of understanding, a voyage into the heart of the most profound mystery in all of physics. The idea itself seems impossible, a fantasy from a distant world. Yet, the universe is filled with these strange, powerful objects. They are born from the depths of massive stars. They lurk in the centers of galaxies, including our own Milky Way. They are invisible, yet we can see their effects all around them. They bend light. They stretch time. They consume matter with an unyielding grip. To explore what happens when you cross their threshold is to explore the fundamental fabric of space-time itself. To understand the journey, we must first understand the destination. A black hole is a region of space-time where gravity is so incredibly strong that nothing, not even light, can escape its pull. This is why they appear black. They are cosmic traps from which there is no exit. They are not empty space. Rather, they are an immense amount of matter squeezed into an impossibly small area. Imagine the entire mass of our Sun, a star over 1,000,000 times larger than Earth, crushed down into a sphere just a few kilometers across. The density would be unimaginable, and the gravity it generates would be overwhelming. Most black holes are the final, ghostly remnants of massive stars. A star spends its life in a delicate balance. The nuclear fusion in its core creates a tremendous outward pressure, like a constant, controlled explosion. This outward force perfectly counteracts the inward crush of the star's own gravity. For millions or even billions of years, this cosmic battle rages, keeping the star stable and luminous. But all stars eventually run out of fuel. When a truly massive star, many times heavier than our Sun, exhausts its nuclear furnace, the outward pressure suddenly stops. There is nothing left to hold gravity back. In a final, catastrophic moment, gravity wins the war. The star's core collapses in on itself with breathtaking speed. Every black hole is surrounded by a crucial boundary, a line drawn in space. This boundary is called the event horizon. It is not a physical surface you could touch, like the ground or a wall. It is more like a shadow's edge, an invisible threshold marking the point of no return. The event horizon is the precise distance from the black hole's central singularity, where the gravitational pull becomes so strong that the escape velocity, the speed you need to get away, is equal to the speed of light. Since nothing can travel faster than light, anything that crosses this line is trapped forever. Imagine you are in a boat on a wide, calm river that flows toward a colossal waterfall. Far upstream, the current is gentle. You can easily paddle your boat against it and return to shore. As you drift closer, the current gets stronger. You have to paddle harder to stay in place or go back. There is a specific point in the river where the water flows so fast that, no matter how hard you paddle, you will be swept over the edge. The event horizon is like that point in the river. As you continue your fall past the event horizon, you would begin to experience one of the most bizarre and destructive effects of extreme gravity. This effect has a rather playful name, but its reality is anything but. It is called spaghettification. It is the process by which an object is stretched vertically and compressed horizontally, like a piece of spaghetti being pulled. This happens because the strength of gravity changes dramatically over very short distances near a black hole. The gravitational force is not uniform across your body. Imagine you are falling feet first toward the black hole. The gravity at your feet, being slightly closer to the singularity, is significantly stronger than the gravity at your head. This difference in gravitational force, known as a tidal force, would begin to pull your body apart. Your feet would be pulled downward more forcefully than your head, creating an intense stretching sensation. At the same time, the forces around your body would be squeezing you from all sides, compressing your shoulders and hips inward. You would be elongated and thinned out. The intensity of spaghettification depends on the size of the black hole. For a smaller stellar mass black hole, these tidal forces are extreme even outside the event horizon. You would be torn apart into a stream of atoms before you even cross the threshold. One of the most profound consequences of Albert Einstein's theory of general relativity is that gravity affects time. Time is not a constant, universal clock ticking at the same rate for everyone. Instead, time is relative, stretched by gravity, compressed by gravity. The stronger the gravitational field, the slower time flows. This effect, known as gravitational time dilation, is not just a theoretical curiosity. We measure it every day. The clocks on GPS satellites in a weaker gravitational field than Earth's surface run slightly faster. We correct for this to make GPS work accurately. Near a black hole, where gravity is at its most extreme, this distortion of time becomes mind-bending. Imagine you falling toward the event horizon while your friend watches from a spaceship far away. From your friend's perspective, something strange happens. As you get closer, they see your movements slow. Your clock appears to tick more slowly than theirs. Time for you, from their point of view, grinds to a halt. Light from you must struggle to climb out of the gravity well. The light loses energy, shifts toward the red end of the spectrum. This is gravitational redshift. As you fall, it is not just time that becomes distorted, but space itself. The immense gravity of the black hole bends the path of light rays, creating bizarre and spectacular optical illusions. Looking back at the universe you left behind, you would see a strange and rapidly changing vista. The sky would not look like a vast, dark expanse dotted with stars. Instead, the entire universe would appear compressed into a shrinking, bright circle of light above you. All the stars would be visible in this one distorted patch of sky. All the galaxies would be visible in this one distorted patch of sky. This happens because light from all directions in the universe gets bent around the black hole. Even light from stars that are technically behind the black hole would have its path warped so that it could reach your eyes. You would be able to see the entire celestial sphere in a single, distorted window. As you fell deeper, this window to the outside universe would appear to shrink, grow brighter, and shift toward blue. You know, looking forward, in the direction of your fall, you would see only perfect, absolute darkness. After you cross the event horizon, all paths lead to one place, the center. According to Einstein's theory of general relativity, the center of a black hole contains a singularity. This is a point where all the mass of the original star has been crushed into a region of zero volume and infinite density. Here, the curvature of space-time becomes infinite, and the tidal forces that cause spaghettification grow without limit. At the singularity, the laws of physics as we currently understand them completely break down. Our equations give us nonsensical answers, like dividing by zero. This breakdown is not necessarily a failure of the universe, but a failure of our theories. It tells us that general relativity, our best theory of gravity, is incomplete. It works wonderfully well for describing planets, stars, galaxies, but it cannot handle the extreme conditions inside a black hole. To truly understand the singularity, we would need a new theory, one that successfully combines general relativity with quantum mechanics. This hypothetical theory, often called quantum gravity, is the holy grail of modern theoretical physics. Without a theory of quantum gravity, we can only speculate about what the singularity truly is. The truth is, we do not know what lies at the heart of a black hole. The singularity represents a frontier, a place where our current map of reality ends. If black holes are truly black and nothing can escape them, how can we possibly know they are there? We cannot see them directly, but we can see their powerful influence on the space and matter around them. We are like detectives at a crime scene piecing together clues to identify an invisible culprit. One of the most important clues is the motion of stars. By carefully tracking the orbits of stars near the center of a galaxy, astronomers can infer the presence of a massive, unseen object. Their rapid, looping paths can only be explained by the gravity of a supermassive black hole. Another key piece of evidence comes from accretion disks. When gas and dust from a nearby star or interstellar cloud get too close to a black hole, they are pulled into orbit around it. This material doesn't fall straight in, instead it spirals inward, forming a flat, rotating structure called an accretion disk. As the gas in the disk swirls toward the event horizon, friction and compression heat it to millions of degrees. This superheated material glows incredibly brightly, not in visible light, but in high-energy X-rays which we can detect with space telescopes. In 2019, science achieved a monumental breakthrough. An international collaboration of scientists called the Event Horizon Telescope managed to capture the first ever direct image of a black hole's shadow. The image they produced was stunning. A bright, fiery ring of glowing gas surrounding a perfectly dark, circular region. This was the black hole's shadow silhouetted against the bright accretion disk, a direct visual confirmation of Einstein's predictions. So, we return to the question: what would happen if you fell into a black hole? You would embark on the most solitary journey imaginable. You would witness the laws of physics contort and break. You would see time slow for you from an outsider's perspective, while from your own, the future of the universe might flash by in an instant. You would be stretched into a stream of atoms by unimaginable tidal forces. And you would fall toward a central point so mysterious that our science has no words to describe it. It would be a journey of terror and profound, silent wonder. Black holes represent the boundary of our knowledge. They are nature's laboratories, where gravity is tested to its breaking point. They force us to confront the deepest questions in physics. What is the true nature of space and time? How does gravity work at the quantum level? Is information ever truly lost from the universe? Each new observation, each new theoretical insight brings us a small step closer to understanding these dark, enigmatic objects and the fundamental rules that govern our reality. They teach us a valuable lesson in humility. We may never travel to a black hole, but we can continue to look up at